Welcome to this Studiegeneraal evening. It's lovely to see you all here on this cold Tuesday evening. But here it's warm and cozy, and we have a very interesting lecture coming up for you. And my name is Jaap Jansen, and I'm program maker at Studiegeneraal. And for those who don't know Studiegeneraal, we organize extracurricular lectures, debates, lecture series, film and talk evenings, cultural events on a very broad range of topics. And the lecture of tonight is part of our TechLec Series. And in this series we explore the latest developments from the forefront of science and technology. And this evening we are going to travel into space. At least we are going to fantasize a little bit about how it will be, might be, if we could be if we will be able to settle in space. And for example, what will it look like? And will human beings ever be able to settle on places like Mars or the Moon? And how would these settlers feed themselves? That's one of the most important questions. And well, there are people actually doing research on this. And it might seem to be a very far future, but well, people are investigating how we can grow food on places, on very remote places. And one of the specialists in this field is here today, and that's Wieger Wamelink. And I would like to thank you for coming to Maastricht.
That's more nearby than Mars.
He is an ecologist, and he is an exobiologist, and he is affiliated to Wageningen University and Research. And he researches all kind of aspects of growing food in very extreme environments like Mars and the Moon. And it includes not only plant growth, but also aspects of developing closed agricultural systems. But that's what you are going to talk about.
Yes.
So I would like to give the floor now to Wieger Wamelink. Please give him a warm applause. The lecture will take 1 hour, and after the lecture we have half an hour for Q&A. So please keep the questions you might have, and we will end this evening at 9:30. Please give him a warm applause and enjoy the lecture.
Thank you. Good evening to all. I'm very happy to be in Maastricht. My first ever talk here in Maastricht, so thank you for having me over. I'm going to take you on a journey, and hopefully that journey we can make together, and we will end on Mars, at least in our thoughts. But I like to start nearby, and nearby for me is still outside Earth on the ISS. Because I'm going to talk about, if you go to space, what are you going to eat? When you want to live on the Moon or Mars or even on the ISS, what are you going to eat? Now, nowadays in the ISS, the International Space Station, where André Kuipers also went, our Dutch famous astronaut, they still ship in all the food. You can imagine that's costly. It takes time, it takes fuel. It's not very environmental friendly. So if we could grow our crops at the site, then that would be very beneficial, and it would also secure your food. Well, first experiments are done at the moment at the ISS. It's called VEGI. There's a lot of news about it, but it's a very small experiment, because what you see here is the whole experiment. So it's a very small part of the ISS that is dedicated to this. They grow vegetables, yes, mostly salads, of course, and it works. You can see it here. even under almost zero gravity. But we always thought, why grow salads? Because that's not the only thing you want to eat when you are in space. You need more. So why not potatoes, rice or rye, things that really can feed you? That's what we are looking into. So we do more than just salads. But still, it works. And it works in the ISS. They even brought some back to Earth to do analysis because, well, this is the first time we do it in space. Has it the same taste? Simple question, but we don't know. Does it have the same nutritional value as the crops that you grow on Earth? We don't know. And that's of course very important, because if it deviates from the standard we have on Earth, then either you have to grow lots more crops, or you still have to ship in additional food to feed the people that are living in the ISS. So it's very important that it has the same quality. Well, they shipped it back, but the astronauts who were growing the crops, they were told that they were allowed to eat a part of the harvest. And astronauts love it, because normally they get freeze-dried food or tubes with liquid and food in it, and it's not very tasty. Astronauts always lose weight when they go up, and one of the reasons is that they don't eat enough, and that's because the food is not very tasty. Ask André Kuipers, he will say the best moment if you are up in the ISS is when the new food arrives, when they can have a pizza, something like that. But that is only for a couple of days, and then they are back to their normal diet. So food is very important, not only for their weight and their functioning, but also for their well-being. So it's key. So they were allowed to harvest it and to eat a part. The rest had to be shipped to Earth. But I spoke with the head scientist of NASA who did the analysis, and she said, well, I couldn't do everything because the astronauts ate too much. Because they liked it that much that there wasn't enough left for them to do all the research. That already shows how important it is for them to have fresh food. They really liked it. And even up there, where everything is controlled, from NASA, from the States, they check everything, but still they ate too much. But that shows the importance of fresh food in space. And I think when you want to go to the moon or go to Mars, it is essential. We will not survive there if we don't have fresh food. You can ship it in, of course, but fresh food is essential. That's where we're working on. Now, if you go to Mars or to the moon, we will travel there. We already travel to the moon. We people, we bring all kinds of animals with us. Bacteria, for instance. We cannot live without bacteria. We have a couple of kilos of bacteria in our gut, and it's necessary. If you wouldn't have it, you would die. So they are needed. But of course, you also go to the toilet. Then it comes out. And the big question is, if you go to Mars or to the moon, will you contaminate those places? Well, for the moon maybe that's not very important, because there's no life on the moon, so yeah, there is not much influence. On Mars it could already be different, but if you look further, nowadays there's talk about going to the moons of Jupiter, which have icy surfaces, but below there's liquid water. And we want to go there to do analysis to see if there is life. That could be. But if we go there with spacecraft, which are contaminated, then we could contaminate a totally unknown ecosystem for us. That would be the same as what we did in the past when we went to Australia, for instance, or to the United States from Europe, and imported their rabbits and all kinds of plants, which are now a plague. That's something we want to prevent if we go and live on another planet. That's something you really do not want to do. So you have to make sure that doesn't happen. And For that, they did an experiment on the outside of the ISS, so in near vacuum, just in space. The German organization, DLR, they designed a setup where they had all kinds of animals, bacteria, algae, it's late, even teddy bears, and also my favorite lichens, on the outside of the ISS. It stayed there for over 500 days, and then they brought it back to Earth and they looked if they were still alive. And the big surprise was all had at least some specimen that survived over 500 days in space. Now the travel to Mars takes about 9 months, which means if you don't clean your spacecraft very thoroughly, you could contaminate the planet with life of Earth, something you do not want. That's something to take in consideration when going there. But it was a big surprise that they survived. Especially bacteria did very well, and teddy bears as well. Beerdiertjes for the Dutch people. They don't grow, of course, because it's in space, so it's near vacuum, there is no liquid available, but they did survive. So that's already a threat, and that is something you have to take into account, and it's something we normally do not talk about. In the space industry, we just go and don't take these kinds of things in consideration, but I think we should. We don't want to repeat what we did to, let's say, Australia, New Zealand and the United States, where we import alien species, alien in this case, very different link, but we don't want to contaminate another planet if there is life and it could maybe even wipe it out. So it's something to take into consideration before you go to Mars or the Moon. Well, then first let's look at the Moon and later on to Mars to see, I want to grow my crops over there. But is that possible? Well, it's about 400,000 kilometers away. It's about a 2-day flight, so not too far away. Yesterday, NASA launched a vehicle to the Moon, but today I read already this morning that they were short of fuel, so they won't make it. So it's still difficult to go there. India landed last year, for instance. The Chinese also landed last year on the Moon, but we are busy working on going back to the Moon. Well, on the Moon there is no air. So that's already a problem for my plants, because they need air to grow. They cannot grow in vacuum. We've got a lot of cosmic radiation coming from the sun, but also from the rest of the universe, which may influence plant growth. We have to look at that if it is possible. For humans, we know it's dangerous. If there is a solar flare on the sun, then the astronauts in the ISS have to go to either to the Soyuz because it's more protected, or to go to a special area in the ISS to protect themselves. Otherwise they get too much radiation and they may get cancer. So it's dangerous. But how do plants react to that? The gravity is lower on the Moon. It's 1/6 of Earth, and actually we do not know what effect it will have. It's very difficult to test that on Earth. We cannot lower the gravity. That's a big question. But what we do know, and that's a bit of speculation, and we like to do that, of course, is that the maximum growth of plants, trees, is limited by the gravity. It's about 120 meters, and that is because the plants take up water and nutrients from the soil with their roots. It goes up and it has to go into the leaves. Of course, gravity works in the other direction, so it pulls on the water. And the maximum evaporation is about 120 meters, totally based on the gravity. So if you have 1/6 gravity, could the trees be 600 meters high on the Moon? Imagine. But we don't know. Also interesting is that a day on the moon lasts 28 days. It's one moon cycle. The moon always has the same side to Earth. We see only one side of the moon. It circles around Earth in one moon month. That's 28 days, but it's 1 day on the moon, which means it's 24 hours. 14 days light. That's no problem. But it's also 14 days darkness. That could be a problem for plants. Unless, of course, you go to the equators where it's different and we can have almost constant light. But a plant that survives 14 days of darkness, don't know. So there are a lot of things that make that growing crops on the surface of the moon is impossible. So we have to have a solution for that. Then looking at Mars, much further away, and it takes you about 9 months flight at the moment to get there. That's the quickest. We hope to bring it back to 6 months, but it's a long journey. When you arrive over there, the gravity is also lower. It's 1/3 of the Earth. So we still have that question, how will it affect the plant growth? But the day-night circle is quite similar to what we have on Earth. A day lasts 24 hours and 36 minutes. So that's similar to what we have here, which is convenient because plants are used to it. There is almost no air on Mars. There's a little bit of air pressure, but well, we cannot breathe in it. And also plants are not able to grow in that. So also there, it's not an option. And also the radiation there is still present, as on the moon, because Mars, and that's different from Earth, Earth has a magnetic field which protects us from cosmic radiation. This winter also you saw it, you can see actually the radiation coming from the sun during the night, because then the northern light is visible. It lights up, that is cosmic radiation, so you can see it. But it's dangerous, and it also ends up on the surface of Mars. Mars also has no atmosphere. Atmosphere also blocks part of the radiation, so that does not help either. So that is, again, a possible problem on that planet. Now, and here on the moon, I know there is no life, but for Mars, we're still not certain. And then, of course, the question arises, if there is still life, maybe, I don't think so, but given the circumstances, but if there is, can we go there? Can we live there? Can we bring our own stuff over there? Will we contaminate the planet? And is the planet ours, or is it from whatever living being there is on the planet? Well, I don't know, but we're working on it already. So we're going there. And for the moon, I know we already brought bacteria over there, because the feces, the poo, of the astronauts that went there did not come back. It's still on the moon. It's still there. I think the bacteria will be dead now, but they were there. So we already did that, but they're important questions. How are we going to live on Mars or on the moon? Well, I think the ISS will be decommissioned in a couple of years. And maybe it will go to commercial parties, or they will just get it down and burn it in the atmosphere. That's not totally clear yet. But the next step, I think, will be that we have a kind of ISS on the moon. And then I think you have to grow your own crops over there. That is the most convenient and also most logical thing to do. But you cannot do that on the surface just like that. So we have to go indoors, and that is shown here. It looks a bit like a hobbit home. You go below the surface. You need at least 3 meters of surface on top of the of your dome, because you have to be protected from the cosmic radiation. So you will be below ground, but you will be indoors, which is very convenient for me, because I can control a lot of circumstances. I can have normal air pressure. I can have LED lights inside, so I can control that as well, the quality of the light, the intention of the light. And that's very handy for my plant growth. But what we want to do is to use as much as possible resources that are present there, which means the regolith that is present on Mars, soil you could say, although it's not soil, and also the water that is present on Mars and also on the Moon in the form of ice. That's what we want to use, and that is where we do our research on. Now, we have the regolith, we have the ice, and the atmosphere of Mars, very thin, but contains mostly of CO2. Well, we know that, huh? We have it here on Earth as well, it's increasing, but most of it on Mars is CO2, which we can use, of course, for our plants. So you don't have to bring all your air with you, you can use the CO2. There is also a little bit of nitrogen. Well, that's the main component of our atmosphere, so we can also use that to make an atmosphere comparable to Earth. There's a little bit of oxygen as well, so we can use it as well. But, of course, our plants will produce from CO2 also oxygen. So the plants can be a part of that system. On the ISS is now totally based on technical equipment. They do it chemically, turning CO2 into oxygen again. But plants can be a part of that, and maybe even be the major part. Even if you don't eat it, they're already very helpful. Now, what are we working on? We have our dome, we arrived. Now we need to eat. And that's what we're working on. And how we see it is that since there is nothing on Mars or on the Moon, only the regolith and the ice. But for the rest there's nothing. So what we need is a circular agricultural ecosystem, a closed system that is self-sustainable. That's important for Mars, it's important for the Moon, but actually it's also important here on Earth. And especially in the Netherlands, we have forgotten a little bit about that. If you look at how we do our agriculture in the Netherlands, it's not sustainable. We import a lot of nutrients from outside the Netherlands. We produce a lot of meat, but also the feces of the meat stays in the Netherlands and it doesn't go back. So that's not circular. That's something we cannot do on Mars. We have to make it circular. So everything has to be reused, which means we have a plant, in this case a pea, there's a special reason for it, it flowers. Now we already learned in our first experiment, you have to pollinate it. So you can do that by hand, we did, but on a bigger scale you need pollinators, that can be bumblebees or flies. So it's not only about bringing seeds to Mars and grow your crops, it's much more. We have organic waste, because from a pea we only eat the pods. For the rest we don't eat them, but that has to be recycled. We need bacteria to do that, but also worms. We do also research on that, because the worms, they will eat the organic matter. And the poo, of course, is then again manure for the plants. But if I talk about manure, that also is the case for the humans. We eat the pods or the other vegetables, but of course, the feces has to be reused, which means that our urine and our poo has to be given back to the regolith to grow the plants again on. That also has to be made circular. It's also something we do not do here in the Netherlands anymore. We flush it down the toilet and then it's gone, but it costs us, that already costs us a lot of money. Then it goes to a waste processing plant, and there we take it out again with the bacteria. Then we burn it, so we lose it. Totally not circular. That's something, well, we do here on Earth at the moment, and in the Netherlands, of course, we have enough manure from our cows and our pigs and our poultry, but that's something you cannot do on Mars. It has to be recycled. We're working on that as well. Now, in the past we also worked with bacteria, special bacteria, that go in symbiosis with the pea. And what they do, they grow in the roots of the plants, and they can take N2, nitrogen, out of the air and turn it into nitrate, manure for the plants. So in that way we can manure the soil. It shares it with the plants. In return it gets carbohydrates, so that's where the bacteria live on. But it is a total symbiosis, and that's also an important part of our research to see if we can establish that also on these soils, because it would give us an extra source of manure on a site where there is almost nothing. So that's important. We also want to bring fungi because they can acquire nutrients from rock. So if there are no nutrients, they still can free it from the regolith and share it again with the plants so they can grow, for instance phosphate. So this is the system we want to build and what we're working on. And at the moment, well, we have been working on almost all aspects of it, and I will show examples of it and also results, not on the fungi yet. So there's still an opening. If a thesis student is looking to do something in that direction, you're welcome. First, how do we do that? In Wageningen, because I'm here and not on Mars. So how do we conduct that research? There are a lot of rovers on Mars. They have laboratory on board. They do all kinds of measurements on the regolith. They have a photospectrometer on board and they can exactly measure what the mineral content of the soil is, of the regolith. So we know how it is. But still I have a big problem because there has been no regolith brought back from Mars to Earth. It's not here. The only thing I have is a little small rock, and that is a meteorite that came via space to Earth, but we cannot use it. It changed. So it's not here. For the moon we do have rocks over here, a couple of 100 kilos, but if I'm going to use it for my experiments, normal experiments I already need 100 kilos, then of course we would deplete the stock very quickly. It's very expensive, and if we use it then nobody else can do any research on it, so we are not going to get it. But there is a solution for that, and that is this. You see it here for the moon of Mars, the regolith. What NASA did is look on Earth. Where do we have the same soil on Earth that resembles what you would find on Mars or on the moon? That is what we are using for our experiments. So it's a simulant. We are not using the actual soil. And that's important, of course, to keep in mind. How well is this simulant? Well, it's improving. The first generation was mostly used by NASA and also by ESA to test the rovers and to test the suits that are going up to the moon or to Mars. But they never came up with the idea, well, let's see, maybe we can use it also for plant growth. So when I started these experiments about 10 years ago, much to my surprise, I must say, nobody ever did something in this direction. So yeah, we were the first. But it was very, very, very surprising because these simulants already existed since the 90s of the former century. But this is what we use. And the regolith we used is coming from Hawaii, from a volcano, but also from deserts nowadays in the United States. And that, well, resembles what you would find on Mars or on the moon. And since we are growing crops on them, what we actually are doing is growing crops in very harsh conditions on very harsh soils, degraded soils. So what we do for Mars or for the moon could also be applied here on Earth, for instance, to grow crops in deserts to make them fertile again. So it helps our research here on Earth as well. Yes, this is an overview of the nutrient content of the simulants. We also use in this first experiment, which I will show some examples later, a control, you always compare with a control, and in this case our control was riverine sand from 10 meters deep, nutrient poor. It looks a bit like playing, but you use in a playing ground for sand, zandbaksand. That resembles it quite well. And we compared that with our first simulants. You see them here as well. And you see here what nutrients are available for plants in these soils. Now, I want to highlight a few. I'm not going to do that actually because it doesn't go that quick, but first of all you see that there is nitrogen and phosphorus available, N dot and P dot. That's good because plants need that. Nitrogen, phosphorus and potassium are the key nutrients for plant growth. If you go to your garden center and you buy manure, it always says those three in which amount they are available. But if you look more close, plants cannot do anything with that. You have to have either ammonium nitrate or phosphate, which are below. And the content is actually very, very low. So these are very nutrient poor soils. Already only based on that, it is very difficult to grow your plants. Now, there are some other features that are important, and the first one is the soil pH, the acidity of the soil. Now what we see is that the earth soil is quite okay, it's around 7, that's normal. But the Martian is already above 8, which is rather high for growing crops. If anyone has its own garden, I don't hope that you have a pH in the soil of that magnitude, because then plant growth is almost impossible. Now if you look at the moon regolith, the pH is almost 10, which is high. It's very difficult to find any place on Earth where the pH is so high. And if you find some, then mostly there are no plants growing. So it's a really tough soil. Then there's one extra thing I want to highlight, and that is the aluminium content. There is free aluminium in the moon regolith simulant. And aluminium is toxic. Not only for humans, but also for plants. Plants can deal with metals quite well, much better than we, because besides aluminium there is zinc, cadmium, lead, all these things are present in these regoliths, which can be poisonous for us, but plants can deal with it. They store it and they just grow, unless it gets there in very, very high amounts. But aluminium is also toxic for plants. So if I'm looking at this, then my expectations were very low. I thought, well, maybe some plants may grow. So for our first experiment, we selected 14 different plant species, mostly wild plant species, so not crops, because wild plant species can deal with these harsh circumstances much better than crops. Crops need to be nurtured, and well, they do not do well under difficult circumstances. But we had 4 crops. We had tomatoes, we had carrots, we had cress, and what was the 4th? Well, we'll see later. For the rest, it were plants that were growing under harsh circumstances. Now, we had 14 plant species, 20 replicas, and 5 seeds per pot, which in the end resulted in 4,200 seeds, which we wanted to follow on a daily basis, and we hoped that some would germinate. That's why we had so many seeds per species, and well, maybe they would grow, but we were not sure. But it turned out, as you can already see, this is a part of the overview of all those pots. You see a lot of green stuff. And that's not only in the earth control, but it's also on the moon soil, and also especially on the Martian. So all plants germinated, and most of them did grow. So it was a lot of work for us, because we had so many seeds, but we managed. we had a lot of information already on that first experiment. You see, the rye, yes, that was the fourth one. You see here the green that is really sticking out, that is rye. So one of the crops we had. But it went very well. It was really, really unexpected. And the garden cress, after some time, even started to flower. This was on the 5th of May. In Wageningen, a big day, Liberation Day, so everything is closed. Also our greenhouse is closed, so I had to ask for special permission to go into the greenhouse, because the day before I saw something, I thought these are not normal knobs for leaves. This looks like it's going to flower, and that was something we could not have imagined when we started. So I wanted to be there, so I was in the greenhouse. There was nobody else there, but I made this picture. This is the first flowering plant ever on Mars soil. Simulant, I must say, but still. But it learned us a lot, because nice greenhouse in Wageningen, no pollinators inside, and if they are inside, then they're killed, because you don't want them to intervene with your experiment. But we needed them. So what did we do? We did it by hand. We took a paintbrush and we pollinated all the flowering plants. Now, that's something you can do, of course, in a greenhouse in an experiment. That was already a lot of work, but you cannot do that on Mars. That takes way too much time. So that already, our first experiment also indicated we need more than just growing crops. We need much more. We need pollinators and lots of more help from other animals and species. But we were successful with pollinating, because a few weeks later the seeds started growing, and already in the first experiment we had seeds. And you may think, well, okay, nice. But of course having seeds is very important, because that's my next generation. And just growing crops and eating everything, that's not wise, because then you have to ship in every time new seeds. No, we want to have an agricultural ecosystem. And even if we have new seeds, the plants may adjust already from the first start to the lower gravity, for instance, and the circumstances on Mars. So you could also do plant breeding over there when you have seeds, and improve your crop adjusted to those circumstances. But we were very happy with that result. I must say that on Mars it stayed very well, and it was comparable to Earth control, which of course was still very nutrient poor sand, so not the normal potting soil. But on the Moon, regolith, a lot of plants died. So they germinated, sometimes they formed leaves, but then they died. So there was a big difference. And I think that was because of the aluminium, because of the high pH, but also what we learned is that, especially the Moon, but also Mars regolith simulant, they are very hydrophobic. If you put water on top of it, it doesn't go into the soil, it just stands on top of it. And of course that's very difficult for plants then to grow in. In the end, of course, it goes into the soil, but if it's very hydrophobic, we had a nice summer that year, it evaporates also very quickly. Which means we had to water the plants twice a day, and even that was not enough. So, and if you think after that first experiment, well, they had rye grains to eat, or yes, garden cress, we had leaves so we could eat, but the tomatoes, this size, and I'm not talking about the tomatoes, I'm talking about the plants. So that's not something you can live on. So it did grow, but it didn't grow very fast and not very high. And of course that's not enough to feed people. But we learned a lot, and we saw some problems, and in our second experiment, what you see here, we changed just one thing. We added dead plant biomass from the previous experiment to the regolith. As if you would do over there as well, because you have to recycle, recycle, recycle. Something we do on Earth as well. I do it in my vegetable garden as well. Bring the dead plant parts back in the soil, it's healthy for the soil. That solves several problems, and we saw that during the experiments. The water giving lots easier because organic matter is very good in holding water. The water holding capacity of the regoliths goes up tremendously. So that's a lot better for plants to grow. On the moon regolith, aluminium is bound by organic matter. So you lose that problem as well. And of course, it releases nutrients, so it's broken down. I'm not working sterile, so there are bacteria in these soils, and they break down the organic matter, so they release nutrients for the plants. So just one simple addition made a huge difference. You can see it already here. These are only crops now. We've sown 10 different crops in one tray. A very small experiment. But you can see, for instance, the peas, they are in the middle. On the right there is spinach, next to it is the garden cress, then we have radish, but also we had rye, we had quinoa, we had leek crops over there. You can already see that they're sprouting, and if you look carefully, there behind is the grey regolith of the moon, and there also a lot of plants are sprouting and starting to grow. By the way, anyone knows why the moon is grey and why Mars is red? Sorry? Iron, exactly. Yes, it's rust. Basically, the Martian soil is rust. It's up to 25% of iron oxide, and in that case, iron 3 for the people who still remember the chemical science. So it's Fa2O3, which is red. It's the same as the rust on your bike if you don't take care of it. On the moon, it's also rust, but it's iron 2, FAO, and that's grey. That's the difference. That's why Mars is red. It's because of the rust. It's one big rust ball. But the crops started growing, and they grew very well. And even on the moon, we were able then to harvest really the first radishes and also the first tomatoes. We have the tomatoes here. The top one is very famous because it was published in many newspapers all over the world. But we were able to grow tomatoes, but also other crops that you could eat. And well, I talked about the size of the tomatoes from our first experiment. That was this size, but that was the whole plant. These tomatoes look nice, but still they were this size, so not too big, and they should have been this size. So yes, a huge improvement, but we were not there yet. And I must say, we still struggle to get the results that you would have on normal potting soil in a greenhouse here on Earth. And that's one of our goals, of course. Not only to have the nutritional value, which I already said before, but also to have the same yield. Because if the yield is only half, then you need twice the space on Mars or Moon to grow your crops. And that's difficult because everything over there will be difficult. So the more efficient it is, the better it is. Well, then it was time to taste our first crops. Now, I already said there's a bit of a problem with it because they can contain heavy metals, like zinc, cadmium, lead, and that's not very healthy. Well, first thing I thought of was, well, let's get some students, let's test them on them. They can taste and then see what happens. But I'm told that's not allowed, at least not today anymore. So then I came up with the idea, well, let's invite someone who does stunts. This is Rachel moet ik zeggen. She is famous for a Dutch children program that she does all kinds of stunts. So she came over to Wageningen and tasted the first radishes. Now what you see here is a bucket. We cleaned the radishes because the radishes, they're growing partly above ground, partly below ground. So there is regolith on it. So we cleaned it thoroughly because you don't want to eat the regolith because that's where the heavy metals are. So they were really clean, but our crops, they're quite spicy, especially the radish. And she did not really anticipate that. So she tasted, and she thought, oh, nice, and they are nice, I can tell you. But then the spiciness kicked in. It was really spicy. She thought, oh, this is hot. What to do? Oh, there's a bucket with water. Let's drink from it. And I told her beforehand, don't drink from the water where you cleaned the regolith in, because they're the heavy metals. But she did. Anyway, it's recorded on film, but I can tell you she survived. She still makes programs, so that went very well. But of course, that's not how we do it. We tested it extensively first. We looked at heavy metals. We looked at the content of all the plants. We looked at over 600 plant components, not only at the heavy metals, but also at carbohydrates, protein content, flavonoids, all those things that also give taste, but also nutritious value. And well, here's an example for some of the analysis of the heavy metals, and you can see that sometimes it's higher than the Earth control, which we have on the left, in the middle the Moon, and on the right you have the Mars one. We looked at iron. Well, it's a bit higher in the Martian soil. Well, I told you already, a lot of iron in this soil, so that makes a little bit of sense. But the cadmium is even lower. That also is for chrome and also is for the lead. And then the ecologist of me is awakened, because then I think, how is that possible? It's even lower. And what we're using nowadays as control, earth control, is earth potting soil. You buy it in your garden center. But of course, in the past, everyone drove a car with a combustion engine, and that was all leaded petrol. That lead has gone into the air and also contaminated, well, basically everything here in the Netherlands. So it's even in the potting soil. And you'll find that back in your crops, because lead stays where it is. And you cannot get rid of it, at least not easy. And the what I already said, the regoliths we use, they come from deserts, sparsely populated, so it's much cleaner over there. So that again told me something. If you pollute your surrounding, then it will come back, even in your food. Now, to reassure, this is all way below the maximum threshold, so it's safe to eat, but it tells me something. So, establish that we can eat it. Now, I have a little movie, so I have to step over there to start it. This movie is about applying earthworms on Mars. We want to use the worms to eat organic matter, to bring it back into the soil, and the poo of the worms is then again manure. But we use worms for other things as well. And I'll start it. Come on. Yeah, it starts. Now, on the one side you see garden cress seeds. They are germinating and they are growing roots. On the other side you also see the worms. So you can see their activity. They go up, they look for food. There's also food in the soil. They eat it, but they also dig burrows. And that's very important for me as well, because the burrows again help us with watering the soil, because the water can enter the soil much easier. And also, because of the burrows, oxygen can get into the soil, which is also important because roots of plants need oxygen. Otherwise they cannot live. So these worms are very important. Well, and if you want to, you could eat them. But, well, I would not recommend it, but it is an option. What you also see is that the garden grass is growing nicely, and that you also see that they form the side roots, and that's where they take up the nutrients. So it's looking all good, but what we also learned from this is that you see that the worms sometimes go up, they disturb the plants. And that's something you don't want. So in the next experiment we will add the worms later. So first get the plants established and then add the worms. That's possible because we do experiments. It's not possible to do it outside. Although there are a lot of agricultural lands nowadays that are lacking of worms, and that is already giving problems here in the Netherlands. Also nice, if you have a very wet spot somewhere in the city, and we were asked to help out in Rotterdam in the Netherlands, where they had a big field that always was flooded with water. And they wanted to solve the problem because, well, you could not even play on it. We had a lot of rain the last days, but what helps then is to add worms. And that's what they actually did. So there were, I think, over 1 million worms released over that field. They started digging burrows, and then the water problem was solved. It's something you can easily do here on Earth as well, and it really works. It's a very simple solution, but it worked over there. And of course some birds also like it. They're eating them. Now, we also did experiments with supplementing nitrate via bacteria. You have those rhizobium bacteria. They live in nodules, small little roots, and I can show you a picture later on. You actually can see the bacteria. They live in symbiosis with the peas, and we wanted to test if that really works also in Mars soil regoliths. Experiment done by Stephen Pilon, one of the students, thesis students. So he had the peas and he added the bacteria as well. And the idea is that the bacteria go to the roots and that they are going to live there. And that worked. You can see it here. And I'll try if this works. Yeah. You can see here knobs. That's where the bacteria are. So you can actually see them. They are in there. They take N2 out of the air and turn it into nitrate and give that to the pea plant. All legumes are able to do this if you add the right bacteria. So this is how we can manure the soil as well. There was not much there, but we can add it in this way because they take out the N2 from the air and turn it into nitrate. It's one of the ways we want to manure the soil. And the first steps are looking good, but sometimes it does work and sometimes it doesn't work. So it needs still much more research. Yeah. And now we're getting to us. Our urine. That has to be recycled as well. Now, to do that, we don't use the urine, and don't think that we have a greenhouse and that every day I go there and pee over the plants. That's not how we're going to do it. There's several reasons for it. First of all, it doesn't look nice, but also, hey, gave it away. Urine contains a lot of stuff that you don't want in your system. The urine we use is struvite. Struvite is a crystal magnesium ammonium phosphate. So there is ammonium in it, which can be used as a nutrient, and phosphate. And it's released from that crystal to the soil slowly. So you can put it at the start of the experiment in the pots, and then it's released slowly, so during the whole growth process you have nutrients available for the plant. It helps. But what's also very handy is that the struvite is pure. So it does not contain any contaminants. It's purely magnesium ammonium phosphate, and that's important. The struvite we use comes from Dixies, and that is collected at festivals in Amsterdam. You can imagine that in urine from festivals in Amsterdam there are more substances than normal, and we don't want that in our system. So that's why we use struvite, because it's pure. We don't have that contamination. But of course this may seem funny, but urine can also contain remnants of medicine. You have to be careful with that as well. You don't want to have that in your food system. That's also a reason to use struvite. Now, we applied that to the plants, in this case green bean. Well, on the left side you see a plant, it's yellow, sorry. It has nothing to do with the urine itself, but it doesn't look very healthy. That only got some organic matter with the regolith, but nothing else. So it did grow, it did form a bean, but you can see the yellow leaves, it's not growing very well. On the right-hand side, you see one of the plants that's growing on struvite, on struvite as addition on Mars regolith as well. Well, I didn't even have to measure to see that there is a huge difference and that it actually works. The harvest was unbelievable, especially on the moon regolith. We never had such a high harvest than after adding ammonium and phosphate in the form of struvite to the plants. So that worked really well. So our urine is actually very valuable. It's a very, very good manure. But that's only half of the story. Of course, we have our poo as well. And the first one who donated his poo is well known in the Netherlands and also in Belgium, Tom Waas. He visited us. You can look it up if you want to. It's still broadcasted now and then. He donated his poo for an experiment. It was processed, it's fermented, because you have to make sure also that there are no bacteria in it alive anymore. There can, for instance, be E. coli is in your poo, and you have to be very careful with that because you can get sick if you get it in a small wound or whatever. So it's fermented, but also on Mars it's easy to process because, well, we could also put it outside because it's very, very cold. We've got cosmic radiation, so in the end all the bacteria will die there as well. But he donated his poo, we fermented it, and we put garden cress on it, and that grew as well, very well. And actually, we knew that. Hey, that's nothing new, but we still have to test it. And nowadays, this is not allowed anymore in the Netherlands. It is allowed with your own poo. So if you have your own garden at home, you're allowed to add your own poo to your garden, but only your own. You're not allowed to do that with your neighbor. That's against the law. And I still remember that my grandfather did that. So as a little child, when we got there, somewhere in spring, we could see that he emptied the storage of the poo, which was a year old, so also fermented and processed. But then we went there and he added to his soil. We ate also from that vegetables, of course. But we could see that he did it because then to the soil was always the toilet paper sticking out. So you could still see that. But it works, and it is very old knowledge. We did it in the past, but we don't do it anymore. And that's a shame. By the way, the label I still have because it's signed by Tom Waas, and I still keep that. Yeah. Now, almost to the conclusion, I talked about cosmic radiation. That could be a problem. And we did some experiments at the University of Delft. They have their own small nuclear power reactor, and they can make all kinds of radioactive elements. For instance, cobalt-60, which is we used, it emits radiation, gamma radiation, the same what you get when you take your picture at the dentist. That's the same, and we did it in such a way that it resembles the radiation that you would get on Mars, and we tested that on the plants. And this is the setup. You have to be careful, although the dosage is not that high, still have to be careful. So the plants are inside a leaden, what we call castle. Nienke Tak did that research, you see there on the left, and you see the plants over there, and they were irradiated during the whole growth process. And the idea of all people, also by NASA and ESA, was this is not a problem. If you look at the buildings that you see, the design of the greenhouses, you always see that it's just a little bit of glass and that's it. But that will not block cosmic radiation. And you see here, the plants are growing, but what we saw was brown parts, yellow parts, dwarf growth, very strange growth, curled leaves. So you saw all kinds of effects. Plants did not die, but they didn't grow as well, and that's something you don't want. You want to have it as efficient as possible. And we didn't look yet at the DNA. That's of course the most important thing to look at, but we didn't do that yet. We need more research on this, but there's a huge indication that cosmic radiation also will affect plant growth negatively, and that's also why we have that Hobbit home here as a poster as well. There's a reason for that. We have to protect our plants as well. So for them also below ground. Well, I always thought you will be vegetarian on Mars or on the Moon because that's most efficient. Let alone bring a cow or a chicken in a spacecraft for 6 to 9 months to Mars. How on earth are you going to do that? Difficult, but it's also more efficient. If you want to raise a cow, you need a lot of area with grass, which we cannot eat, and a cow is very inefficient in turning what they eat into what we can eat in meat. So it's very inefficient. So that's why I thought you will be vegetarian. But then Lotte came to me, she's here in the audience as well, and said, no, we have insects, and insects are very good in turning in what they eat into biomass of insects. Turnover rates can be 50 to 90%. And of course their poo can also be used again then as manure. So she set up an experiment to try if we could feed, in this case the lesser mealworm, on parts of plants that we do not eat, grown on Mars regolith. So is it good enough to grow the lesser mealworm on? Now here on Earth we also grow lesser mealworms. You can buy them, you can eat them, but they're grown on very high quality food, actually things we could eat as well. So that's not very circular and not very efficient. If we could get them growing on what we used to call waste products, organic matter that we don't eat, that would be very beneficial in our system. And you would have some animal food, and there's a reason to go for the lesser mealworm because it contains all essential amino acids that we need and we cannot build ourselves, and it is very, very high in protein content. It's comparable to milk from cows. So it's very nutritional and it could be a very, very good addition to your further vegetarian meat. Well, you can see them here, and I'll start this as well. I think they are always very funny. Look at them. They move, they curl, and they eat. You can also see their poo, but they did grow. And on average, they did gain weight, which is good. But they're also cannibalistic, and they eat each other when they don't have enough feed, and that is what we saw. In total, we started with a certain amount, and at the end we had less. So on average they did grow, but in total the biomass did not increase. So there's still a lot of research needed, and we're working on that at the moment. A new experiment started a couple of weeks ago. But it could be a very valuable addition, and if it works out and we are able to let them grow on waste products that we do not eat, that's also interesting for here on Earth, because they now eat chicken meal. Yeah, that's very valuable food, and if they can at least partly live on waste products, that would be very good also here on Earth for our cycle. Now, recently we set up a new website with all of our information. So you can visit us, you can follow us, our experiment. There's a reason why this is here, because our research is totally funded by gifts and crowdfunding and selling of merchandise. So that's how we managed to keep the project going already for 10 years. But we also have nowadays a web shop where you can buy our merchandise, and you can also follow us. And we are on Instagram, Twitter, and on the website. So it's also possible to follow us. And if you support us, one of the things we did for our funders is that after we tested that it was safe to eat the crops, we invited them over to Wageningen and we had the first Martian meal. So we used the crops that we harvested from the experiment to make an actual meal. A 3-course meal, and it looked like, it was very nice, and it looked like almost if you were in a Michelin star restaurant. Thank you.
Thank you very much, Mr. Wamelink, for your lecture. We have till approximately 9:30 for questions. And I was wondering, can the knowledge gained from your research, can we also apply it to improve agriculture on Earth, actually?
Yes.
Deserts, I'm thinking of deserts.
Yes, well, yes, because the regoliths we use, they come from deserts nowadays. The first one came from Hawaii, from a volcano, which is also kind of desert, by the way, because nothing is growing there. But the ones we use today are coming all from deserts. So actually what we're learning is how to grow crops on desert soils. And we actually already did an experiment with Sahara sand in a project to see if what we learned from these kind of projects, if we could use that to let crops grow on Sahara desert sand. And we were quite successful. But you first have to know why there is nothing growing on the Sahara sand. Well, water of course is obvious, but there are other things. There is no organic matter anymore. It's very salty, the soil, and those kind of things. And that's also what we find in our experiments. And yeah, we learned how to solve that. You can use it. And then it will be more sustainable if you would do something like this, because what they do now, if you look at Egypt or Saudi Arabia, they're growing crops in the desert. What they do is they pump up historical water and they use it to grow their crops. You can see it if you look at Google Earth. You can see those circles, and that's there's a pump in the middle, and then the water is spread in a circle with an arm on the crops. Outside nothing grows, but that water will be depleted within 100 years, so it's totally not sustainable. And the way we do it, we improve the soil, which makes it hold longer the water. Totally different approach, and we think that would be much better.
Yeah, but water is the problem, of course, in the desert.
One of the problems, not the only problem.
Biggest problem, yeah.
Yeah, but here also in the Netherlands, and that's also coming from Wageningen, of course, what we show is that you need a sustainable agricultural ecosystem. And we've forgotten about that here in the Netherlands. We use a lot of pesticides, we use way too much manure, we use artificial manure, which is very salty. So almost all life in an agricultural field is gone. It's more or less dead, and that is becoming a big problem because we already see that the yield is going down because of this, and it causes problems. Because also plant roots cannot penetrate the soil if it's very compact. For that you need worms. To make it open. And you need organic matter in your soil also to counteract the carbon dioxide and the global warming. Well, that's a lot of things you can learn from things like this.
Okay, yeah, we'll go to the audience now. Does anyone have a question? Yes.
Yeah, you talked about radiation in plants, and I'm thinking, can't you learn plants to better withstand radiation? That over generations they would be able
Yes.
to grow normally.
Yeah. Thank you. Yes, we can. That's also one of the ideas, and not only to protect the plants, but also to protect the astronauts, because they also have to be very careful. And what would help if we could get vitamin E and vitamin C levels up in the plants, because vitamin E and C help with making you and also the plants safe from the radiation. What happens with radiation is that the radiation comes in the plant, it produces a radical, mostly an electron, and that electron can be captured by vitamin E and C complex and neutralize it. So that would help the plant, and you could look in that. Flavonoids can do that as well, but it also, if you eat it as a human, it would also protect you from cosmic radiation.
Well, thank you for your presentation. It was very nice and interesting. I was just wondering why you went for crops and not just pioneering vegetation instead.
What instead?
Pioneering vegetation, like...
Yes. The first simple question is, of course, you cannot eat them. But in our first experiment, we used pioneer vegetation. I didn't go into detail in what species we used, but one of the species, for instance, Sedum reflexum, you can buy it in the garden center and put it in your garden. Very nice plant, yellow flowers. It comes from the dunes in the Netherlands, which are very harsh circumstances because that's also no organic matter. It's sand, nutrient poor, sometimes also salty. We use them as well, and actually that was one of the plants in the first experiment that grew best. So we did look at as pioneer plants, and they work very well. And there's still maybe the idea when you start over there with nothing, to see what kind of species, maybe even the pioneer species, to start with, and then go to the next stage and growing your crops. But well, if possible, I would like to use, of course, crops as well. But that's an option. One of the things we're looking in at the moment as well, related to that, because the soils are salty, quite salty, is that we use, at least quinoa now, new experiment, which can take up salt from the regolith, and they store it in the lower leaves, so you could even harvest them. And then you could also eat, of course, the seeds of the quinoa. And there are some other plants, lamzoor, for instance, we have here in the Netherlands in the salt, which you can also eat. And we're looking into that as well. So we're looking at several things to use to get that first stage going. And that's really important, because that's, I think, the most difficult phase, to get that soil and regolith and turn it actually into soil.
Yeah, well, I had that. Yeah. Hello. Yeah, so I have a quick question. Why can't we just like terraform the surface of the planet? I mean, you've been asked that probably. Is it just too difficult, or is
yes?
Yeah.
Yeah. The idea is still there, and some people think that is possible. I think that with our knowledge at the moment, it's impossible to terraform Mars. I don't know if everybody knows what terraforming of Mars would mean. That means that you try to green the planet. So you're not going in a dome like I suggested in our poster. Buy it. But you do it on the surface. But there are several problems. There is no atmosphere, so you have to make an atmosphere. Wait.
Greenhouse effect, wouldn't that take place? Greenhouse effect if you terraform?
Yes, but there is almost no air.
Okay.
So you have to make air as well. But the main problem is the radiation. In the past, we've been quite sure that Mars looked a lot like Earth, with oceans, with water. There are a lot of evidence that there were rivers and even oceans on Mars in the past. You can see that at the soil and the shapes of the streams, they are still visible. So, but why did Mars lose its atmosphere? That is because the magnetic field has gone. And the magnetic field protected Mars from cosmic radiation. And if cosmic radiation comes in, it ionizes the atmosphere. And if the atmosphere is ionized, it can leave Mars and it basically floats into space. That's why, well, since the magnetic field has gone, Mars has almost no atmosphere. It still leaks atmosphere, and it's still filled. For instance, there is still a little bit of water in the atmosphere, but it's still evaporating from the soil, so it's still losing water, but because that's ionized and then goes into space. And that's the main problem. So we have to solve that problem And then you could think of terraforming, but there is no knowledge of how to do that. Actually, I have an idea about that.
I would like to hear it.
But that's really science fiction. But you could, because Mars has a lot of iron oxide. So if we could put on the surface of Mars a lot of robots that could melt the iron oxide and turn it into iron and do that from pole to top pole and make basically a big magnet. Then you could get a magnetic field. The only thing is how to activate that. Well, Mars has a little bit of air and has storms. They can be planet-wide, and in those storms you get lightning. So maybe that lightning can be used to magnetize the iron. But this is of course totally science fiction, but this is the idea I came up with. But until you solve this problem, it's impossible. Whatever Elon Musk says, because he's talking about that, but it's impossible.
Good evening. I have two questions. First one is how do Luna and Martian Soul compare to Antarctic Soul, the only uninhabited continent on the Earth? And my second question is
maybe first that question.
yes.
Yeah. Okay. So, there is a difference between lunar and Martian regolith. Big difference is of course the iron, iron 2, iron 3. But for me more important is that the lunar has aluminium, Mars does not have it. And a second thing is, I didn't talk about that, but lunar regolith is very sharp, and that's a big problem for my plants. That's also one of the reasons why they don't grow that well. And that is because the regolith on the moon is totally made by cosmic radiation, because you got the rocks, and due to cosmic radiation they fall apart in smaller particles. But there is no weathering on the moon, so there's no wind, there's no water, which make those particles less sharp. And that's a huge difference, because those particles actually puncture the roots of my plants and they start leaking, and that's a big problem. And the second, if this answers your question.
You forgot about how does Antarctic soil compare to lunar and Martian soil?
The Earth soil.
On Antarctica, that's the continent of ice. How does that compare to Martian and lunar soil?
Sorry, what?
Yeah,
Antarctica.
The icy continent.
I don't know the answer to that.
Oh, sorry. Okay.
No.
My second question is because of unstable agriculture, so floods and droughts are worsened by that. Floods and droughts.
So floods.
Yeah, the too wet and too dry. That's what it because of our unsustainable agriculture.
No, sorry, I don't understand yet.
I ask if unsustainable agriculture worsens droughts and wet periods because of soils becoming infertile. And floods, the opposite. But when it's too wet.
Yeah, okay. Droughts are a problem. I already talked about the first experiments we did, that it was very hydrophobic, the Mars and Moon regolith. That is a problem. Flooding is no problem, because then you gave just basically too much water. So you shouldn't do that. But if you do that, it is also a problem, because it flushes out your nutrients. So you have to be very careful with that. That also happens here on Earth, of course, that you flush out your nutrients, especially the ones that are very valuable, like potassium, for instance. If you have a lot of water going down, which we have, for instance, in the Netherlands on the Veluwe, it takes with it all the soluble nutrients, and that's especially potassium, but also calcium and magnesium. Now, calcium and magnesium are present in the regoliths in huge quantities. So I don't think that will be a problem, but potassium could in potential be a big problem, yes. Compared to Earth, well, we had a lot of rain lately, I don't know if you noticed, more than normal. That also could cause its problems here on Earth, because on the Veluwe, again, sandy soils, it takes with it a lot of nutrients, which are flushed out, so it becomes less nutrient rich, more difficult for agriculture. So that's here. Droughts are always a problem. And you can see that, as an ecologist, I like this question, of course. You can see that, for instance, in 2018, the birches in the Netherlands, they started to die off. And that process is still going on. So there's a huge effect of it. So you have to be very careful with it. Yeah.
Why has Mars no magnetic field anymore? How it disappears?
Well, I'm not a specialist in that, although maybe my previous answer did suggest something else. And actually, I don't think we know it for sure yet, but I think the most common idea at the moment is that the core of Mars is not liquid anymore. And that could be essential. Earth has a metal central part, which is important for the magnetic field, and around it there is a molten core surrounding it. And that together gives the magnetic field. And the idea now is that there is no, so that core is still there on Mars, but there is no liquid phase anymore around it. And since that is gone, most likely that's why the magnetic field is gone. This would also imply that Mars has the highest volcanoes in our solar system. Olympus Mons, depending on how you measure it, is 23 to 28 kilometers high. But at the moment the idea is that the volcanoes are also inactive. So there is no activity anymore, so no lava. And most likely that is what's happened, but yeah, it's a bit of speculation as well.
We will do two more questions, one for you and one in front.
So you talked a lot about the conditions of the composition of the regolith. Could you maybe explain a bit more about the atmospheric considerations that need to be made? Or, for example, how would you create a suitable atmospheric composition in the habitats on Mars?
Mm-hmm.
Because the Mars atmosphere is very low in, for example, in nitrogen, and you mentioned nitrogen-fixing bacteria.
Well, basically there are two options. Either you bring your atmosphere from Earth. That's an option. I already see that you don't like it. And I can understand that, although we have a lot, and we only need a little bit. That's, by the way, how they do it on the ISS, of course. The other option is somehow to make it at the site. And then there are still several options. One is to use the atmosphere that is there. That is possible on Mars. We have to change the mixture totally, but it is an option. The other option is that you use minerals and you release oxygen from the minerals and other N2 from the minerals. That's also an option. The easiest one is, of course, to use the atmosphere over there. But that's not an option on the Moon because there is no atmosphere. So you have to bring it, either you have to bring it or you have to make it there.
So you would actually, in the second...
Wait.
Thank you. So in the second option you mentioned, would it be something like you would release, in the case of nitrogen, some of the N2 from the minerals, and then you would sort of bring it back into the soil with the bacteria, so that the roots could, and that would create the circular system?
Oh yes, of course. That is one of the options. that we want to go to, that you use the bacteria and the plants to recycle everything. But that's only possible if you have a fully sustainable ecosystem over there.
Right.
You have to start off with nothing. So you have to make your own atmosphere at the start.
Thank you.
Yeah.
All right. You have a question too?
Have options not including soil been considered, such as hydroponics, but maybe a reduced system of hydroponics?
Yes. I skip them. If I give a lecture of 1.5 hours, then it's in. Of course, hydroponics and aeroponics even are also options. Hydroponics is, of course, growing crops on water or maybe an intermediate tissue as well. You have to bring that, by the way, because it's not there. Water is there, so there's no problem. Aeroponics is that you spray your plants basically and that they grow from the mist that you give them. Yes, and I think all of these options will be used when you're over there. There are several reasons for it, but there are also very good reasons to use the regolith. Because I've shown you a sustainable agricultural ecosystem. You have to recycle everything, organic matter as well. And that's easiest when you do it in soil. Otherwise you have to break it down chemically and to make new nutrients and to add that to your liquid phase. That is of course still possible, but it's also complicated. It's not as easy as you think it is. And another reason is I want to grow potatoes, for instance, on Mars. I like them, French fries, but growing potatoes in liquid phase is very difficult. It's possible, but it's not easy. So there's a reason also to do that in the soil. And we've tried it. The potatoes grow very well in regolith. They really like it. And potato is one of the key plant species in my system. And it is because the potato has a very high nutritional value. Compared to salads, it's nice to have them, but you have to have energy. And potato is very good in that. And also, potatoes don't need much space. This space is enough. If you want to grow rice or you want to grow rye, it needs much more space. So it's very efficient. And well, what we tried in one experiment is to break the world record in growing potatoes in a greenhouse. And we managed to go from potato to harvest in 10 weeks time. And I think we can bring it down to 8 weeks if we want to. That's really quick. Imagine that, let's say you can have it in 10 weeks to 12 weeks in the greenhouse here. You can have 4 harvested on Earth. By the way, in one Martian year that will be then 8 harvests, because Martian year lasts twice as long. So it's very, very efficient, and that's also important because everything is difficult, and you have to build everything over there. So the potato is important, not because I like French fries, but also because it's really, really important in several ways.
Okay, I would like to thank you once again for this beautiful lecture and for answering all these questions. I would like to thank you for your questions and for attending this lecture. I would like to announce 3 upcoming lectures. We have this Thursday a Dutch lecture about the biological clock. On Monday we have a lecture about children in armed conflict, and on Tuesday we have a film and talk evening about documenting the Holocaust, and that's because of Holocaust Memorial Day on the 27th of January. So please come to the next activities of Studium Generale. One last applause for Wieger Wamelink. And have a look at the merchandise.
Yes, you can support us.
Come, support.